Good morning. We are moving on. We're headed into chapter 6. I know this course is just flying by, right? So make sure you're staying caught up. You should be good on everything through chapter 5 now. I know there's a lot of stuff. Well, there's a lot of stuff everywhere. The kinematics chapters 2 and 3, and then the dynamics chapters 4 and 5. And there's just a wide range of applications now, a wide range of kind of situational homework problems that you can be looking through, the examples from the lecture, the homework problems. There's some practice problems posted for preparation for the midterms that are always coming up. And moving on into chapter 6, we're going to start looking at gravitation, Newton's synthesis. We'll talk a little bit about how our formulas of gravity came about. Great picture. Here we are with the space shuttle orbiting the Earth. There's a good picture of the moon. You can see a few stars. You can see a lot of stars. And then here is planet Earth. So yeah, that's a great shot. So we're going to be looking at Newton's, the formula that Newton derived. And the formula, we're already using a formula for gravity, but we're going to see a more general version of it. So here's Newton's development of the force of gravity. The force of gravity is exerted at all of these locations around the planet. No matter where we go, we find out that there's a force of gravity. The value of g, for example, is really similar. So the first recognition here is that gravity is due to the presence of the Earth. And then Newton looked out away from the Earth and said, what if the force of gravity that everybody experiences near the surface of the Earth is the same force that's holding all the planets in orbit around the sun? Or in this example, that same force that's holding the moon in orbit. So this is kind of Newton's synthesis, I guess. The idea that one force of nature behaving in a certain fashion could explain local gravitational effects on the surface of the Earth, as well as the gravitational force exerted on the moon by the Earth. Now this diagram is showing that gravity works in a manner where, at least the formula we're working from, assumes that both objects experience the very same amount of force, and they say that the forces are instantaneous, and that works well. None of these objects that we're looking at are moving so quickly where we have to take any kind of time delays into account. The formulas that Newton developed we're still using these today, right? Those are the formulas we're using 350 years later. About 350 years we're looking at here. And for 200 years, there were just no known exceptions. And now we understand that gravity is more complicated than the Newtonian force formula. The formula that Newton came up with doesn't continue to work well under extreme conditions of really high speeds and very extreme gravitational fields. But other than that, works really well. You know, 99% of engineering done is based on these formulas. So let's get moving with that. There it is. There's the formula right there. We didn't have to go very far. Newton came up with a description of gravity, a formula that said the force of gravity acting between objects depends on how much mass each object has. Not just one of the objects, but both objects. So if I were to calculate the force of gravity acting on the moon, I would need to know the mass of the Earth and the mass of the moon. Now, r here is distance. And whenever you see little r, we just got through chapter 5, and in chapter 5, r was radius for circular motion. Chapter 6, r is not radius. R is distance. So you've got to start thinking in terms of distance. It's not radius. I wrote this in a really big font, or a really big point, and I capitalized the knot and I put a highlighter around it. R is not distance. R is, oh great. R is not radius. You have to think generally as R is a distance. We'll talk about that more. The big G here is the gravitational force constant, the universal gravitational force constant. And that says no matter where we go in the universe, we're imagining that gravity behaves the same way. So the amount of gravity acting between two objects, so I need to have two objects to experience this gravitational force. And our assumptions are that the forces will be equal and opposite. So the moon exerts a gravitational force on the earth exerts a gravitational force on the moon. The force constant value is measured to be 6.67, 10 to the minus 11 newtons meters squared per kilogram squared. And part of that, that depends on what units we're working in. And if we're working in newtons meters squared per kilogram squared, that's the number we get. Now, what this also says is that everyday objects, like this book and this mug, those both are exerting gravitational forces on each other also. So the cup and the book are exerting forces. When we plug those in, it turns out that the forces are really, really tiny. Now, in very sensitive labs, it's possible to go in and measure that force. In physics, force C actually will come back and do a gravitational force measurement with just some metal spheres that are just a couple kilograms. And under very careful conditions, you can actually measure that gravitational force. All right, that's the formula. Everything's going to come down to this. So let's get moving and look at some examples here. And here is a picture of that setup. Now, I don't know if this is the best picture. So in the labs that we run to see this, we take a very thin strand of metal wire, and we put a mirror on that, and we put a couple of masses to create a rotor that's not very heavy. This is only a few hundred grams. And then we put other metal spheres nearby that are, again, 1,200 grams, something like that. And you can actually measure that this rotates a little bit as these two objects attract each other. Okay, it's a fairly simple setup. It's originally developed by Henry Cavendish. This is called the Cavendish experiment, and we can use that to measure the value of big G in a laboratory. So you think, why don't we measure G by using planets? Can't we use the mass of the moon and the mass of the Earth? And we really don't know what the mass of the Earth is until we figure out what the gravitational constant is. We can't take the Earth and set it on a scale. Can't you look in a textbook and look up the numbers? And you can, but those come from careful measurements and then very careful calculations determine what the mass of the Earth or the Sun or the Moon or Jupiter. Those are based on knowing what these values of big G are. All right, can you attract another person gravitationally? A 50 kilogram person and a 70 kilogram person are sitting on a bench. What's the magnitude of the gravitational force that they each experience? I'm sure you've had this happen in class. You sit close to somebody else and you feel this gravitational force and you both tip over from the gravitation. Well, maybe, maybe not. But here are two people. Let's say they're separated by 1 meter. Gravitational formula, that's the general formula. It's, those earlier chapters we were using mg, but now this is a more general formula where we can calculate the force acting between two objects. We'll see what the connection is here in a bit. So we will come back and see how this relates to the formulas we've been using. Now m here is the mass, r is the distance, and we got to use center to center distance. So I'm going to take the center of this person and the center of this person and say the center to center distance is 1 meter, and they're both going to experience this much force. If I got 50 kilograms and 70 kilograms, the force acting between those two people is going to be 2.3 10 to the minus 7 newtons. It is going to be 233 nanonewtons, where nano is 10 to the minus 9. So nanonewtons are really small. So it's not much force for everyday objects. The forces are really big if you've got things the size of planets, but if you have things the size of people, not so much. So the forces aren't extremely large for that. Here's another example. We've got a spacecraft this time. Now this is a little, I think I'm understanding it. This is this is a radius of the Earth. So the distance from the center of the Earth to the surface is r. Now we're going to take this distance from the center to the surface and we're going to double it. So we're going to take that distance and we're going to double it, and now this spacecraft is located a distance of 2r from the center of the Earth, where r is the distance from the center to the surface, and that is the radius. So this is going to be twice, this distance is going to be twice the radius of the Earth. So now they're telling us, they're asking us to calculate the gravitational force acting between a 2,000 kilogram spacecraft orbiting the Earth at this distance. Now they're saying little r is 6,380 kilometers, and so we got to double that. Now the mass of the Earth, we've measured that and then done calculations, is calculated and measured/calculated to be 5.98 10 to the 24th kilograms. So here's what's going on. I've got one object, it's the planet. I've got a second object, it's the spacecraft. I'm measuring the center to center distance, and I'm going to call that r this time. And r is the distance between those two objects. Now it's 2 times, I'm going to say big R is the radius of the Earth. So the distance between these two objects is 2 of those r's, and using the numbers that they used and doubling it, I'm getting 12.76 10 to the 6th meters, 13 million meters as a distance. I'm putting in the mass of the spacecraft, the mass of the Earth, and then I'm writing down the gravitational force constant, and then I'm going to plug everything into Newton's equation for gravity. There's big G, m1, m2, here's the distance. I got 4,900 newtons. Okay, so that 2,000 kilogram spacecraft is experiencing 4,900 newtons, and it's out there at a distance of 12 million kilometers, 12 million meters, or 12,000 kilometers, 13,000 kilometers from the center of the Earth. So that's the force. Now both objects, both the Earth and the spacecraft, are experiencing that force. And you go, well, isn't that going to have an effect on the Earth? It certainly is going to have an effect on the spacecraft. Well, let's see. They're both experiencing the same force, but that doesn't mean they'll experience the same acceleration. As far as how much this effect this has on the motion of the object, we want to take the force and divide through by the mass. So the spacecraft's acceleration works out to be 2.45 meters per second squared. And so with that number, then we can determine the radial acceleration. This spacecraft is in a circular orbit. That takes us back to chapter 5, looking at circular motion. And so I'm going to have an acceleration of 2.45, and from that we can calculate how fast that satellite needs to be moving if it's going to maintain a circular orbit. We don't want it to come back down to Earth. We don't want it to leave Earth gravitation and go far, far away and disappear. We want it to stay in a circular orbit, and there's going to be a certain speed, and that's going to be related to the acceleration value. Now, just as an aside here, this 2.45 meters per second squared, that's the gravitational field of the Earth at that elevation. So when we see these things in orbit out in space, the accelerations that we see are always going to be related to the gravitational field of whatever is holding that object in place. Now the Earth also, we said, is going to experience 4,900 newtons of force but to find out how much the Earth is shifted as a result, we divide through by the mass of the Earth, and it says the Earth's response is an acceleration of 8 times 10 to the minus 22 meters per second squared. And you're going, no, that's not going to be noticeable. You know, when the satellite flies overhead, are we going to feel the Earth shake back and forth from the force of 4,900 newtons? And you know, 4,900 newtons for the planet, that's just nothing. You know, its motion is not going to be measurable due to a satellite passing overhead. All right, not much of a wobble introduced from that. All right, let's look at, well, here's an example that feels a little weird, but let's go ahead and look at it anyway. So here is Earth at some point, here's the sun. Here is Earth. Of course, we would want to make them much smaller, scale them way down for the picture. In any case, here is the moon. Now, this is not the scale, because the distance between the Earth and the moon, compared with the Earth and the sun, is really different. It's like, I want to get this right. I want to say this is 400. It's like 400. So the sun is 400 times farther away than the moon. And so I don't think they got the scaling quite right. But we're not going to worry about that, I guess. So we're going to say that at some point in the moon's orbit, things are lined up like this, where the moon is going to be having, there's a gravitational force from the sun acting on the moon, there always is, and there's a gravitational force of the Earth acting on the moon, there always is. And so we're going to take this force and combine their effects. Now, there's some interesting questions here to be considered. Which force is larger? Does the moon experience a larger force due to the presence of the sun, or due to the presence of the Earth? It's much closer to the Earth, but the sun's a lot more mass. So we're going to have to look at that and see. Now, it claims here that the net force on the moon, due to the gravitation... Oh, I'm sorry. Find the net force. This is the mass of the moon. So find the net force acting on the moon. Here is its mass. Due to the gravitational attractions from the Earth and the sun. And they've given us the masses of each one. And then they're assuming this configuration. What they want us to do here is they want us to go back and use vector analysis. So if the moon is being pulled this way by the Earth and it's being pulled this way by the sun, what's the net effect going to be? And it's going to look like this. So I got a force coming from the Earth, a force coming from the sun. I actually drew two thetas in here, theta 1, theta 2. And here are the three masses, the mass of the moon, mass of the sun, mass of the Earth. Now R1, which is the distance between the sun and the moon, is 150 billion meters. Now that also is the average distance between the Earth and the sun, because again, the Earth-Moon represents kind of a double planet system where they're both orbiting each other to some extent. There are going to be times when the moon's a little closer and times when the moon's much farther away. The distance between the Earth and the moon is 384 10 to the 6th. So you can see this is like a factor of 400 difference. And so this much variation in this number won't show up in our calculations. Okay, it will get overwhelmed. So to three significant figures, that's the center-to-center distance between the moon and the sun. Okay, and then this is the center-to-center, so not surface-to-surface, center-to-center distance between the Earth and the moon. I know I keep repeating the center-to-center stuff, and that's because it's hard to get used to, and kind of consistently through the semester, I will continue to have students come up and ask about that, and that will continue to show up on midterm. So I'm just trying to emphasize, when we write these numbers down, it's from the center to center of these astronomical objects. Okay, so the moon-sun force, I'm going to calculate as G, big M1 times little, sorry moon, but you got left with little m, over R1 squared. And I kept everything, calculated it carefully. I got 4.36, 10 to the 20th newtons. And then for the moon-earth force, I got 1.99, 10 to the 20th newtons. And that's kind of an amazing coincidence. It turns out that, you know, the moon is like, the sun's like 400 times farther away from the moon than the Earth is. So if I'm standing on the moon, the Earth is so much closer than the sun, but the sun has so much times more mass. The distance gets squared, the mass does not, and when we look at the numbers, they're the same order of magnitude. So they're actually within almost a factor of 2 of each other. So, all right, the moon experiences the force from the sun and the Earth that are almost the very same. So let's move on then to this diagram. Since we're measuring these at a point in the moon's orbit where these are at right angles, what we can do is we can take F1 squared plus F2 squared. They've already separated themselves out into components, and take a square root. And I ended up with 4.79, 10 to the 20th newtons. So definitely the effect from the sun is bigger, but the effect of the Earth is not insignificant. We have to include both to get a reliable answer to 2 or 3 significant figures. Now, as far as the angles, I decided to do this, I don't know why, just on this one problem. I decided, instead of using cosine and sine, I decided why not use cosine of theta 1, cosine of theta 2. So the angles that are given here, the cosine of theta 1 would be F1 over F, and the cosine of theta 2 is F2 over F. I just thought, here's a different way of using the trigonometric functions. They're a little different. It's good to kind of mix things up. If you get used to the formulas always looking kind of the same, it's easy to get tripped up when things change a bit. So I thought, why not try this? So I did these ratios and then took inverse cosines. And as you see, the numbers I'm ending up with are 24.5 degrees and 65.5 degrees. And if I add those together, what had they better add up to? They better add up to 90, and they do. So that's a good sign. So the net force would be in that direction, defined by those angles that we've come up with. So the direction would be, the net force would be tipped more towards the sun compared with the Earth. The force due to the sun is bigger. All right, now Newton's law of universal gravity tells us this. You can actually use calculus. You can show that if I have a spherical shell made out of something, of mass, so if I have a spherical shell, the gravitational force outside is the same as if all the mass were concentrated at the center. And so when we're using these center-to-center approaches, that's because we're saying that these different objects, the spherical sun, the moon's pretty spherical, the Earth's pretty spherical, we can treat them as a series of spherical shells all nested within each other. Not the different planets, but the individual. So the Earth, you could imagine being made up with a lot of layers, and each of those layers is a spherical shell by itself. If you're outside a spherical shell of material, you can treat the effect of that spherical shell as if all the mass is concentrated at a point right at the center of the spherical shell. Now the flip side of that, which is interesting, is if there's a spherical shell of material that's uniform density, and we go inside, all of the gravitational forces exactly balance out. Not just at the center, but throughout the entire region. So that would be so cool, right? If you could tunnel to the center of the Earth and you could scoop out the center, there would be no net gravitational effect there. Objects that you placed inside that hollowed out region would, there certainly would be gravitational forces taking place, but they would all cancel. So you would be pulled equally, every part of you would be pulled equally in all directions. That doesn't mean you're being pulled apart. It means there's no net force on any part of you. So you could build like an amusement park, right? It'd be no gravity. You could call it Center of Earthland. That would be fun to go visit. Anyway, so if we have spherical objects like planets or stars, and we're doing these center-to-center calculations when we're measuring the distance, we're getting the formulas just exactly right, because to a very, very good approximation, stars and planets can be treated as shells of material, and each shell with a uniform density. So that's a pretty good example. Okay, so here actually is that example. So what that says is if I've got a planet here, and maybe here's an object orbiting the planet, the gravitational force acting on that object is coming from all parts of the planet. It's being pulled in this direction, this little satellite. It's being pulled over here, it's being pulled here, it's being pulled here, it's being pulled here, and here, and here. The closer regions of the sphere are pulling on it more than the regions farther away. If I take a block of planet from over here, and a kilogram from here, and a kilogram from here, the kilogram here is closer and has a larger gravitational force. Now, if you looked at that problem and you go, oh my gosh, that would be a really complicated problem to solve, that would probably require using integration techniques. You would have to go through and break up the planet into little pieces and integrate all those, and that's what Newton did. So this is the problem that led Newton to develop integral calculus. Integration techniques were developed by Isaac Newton when he was making an effort to determine, if I have a mass, a big planet like this, and some object is out here, how can I take into account the gravitational effects coming from all parts of that planet? And it turns out that when you carry that out for a spherical object, you get the same answer as if you took all the mass and packed it at one location right at the center of mass of the sphere, right at the center of the sphere itself. So that's nice in that so many of these examples we look at involve spherical planets or stars, and if we take a center-to-center approach, the formulas are going to be very, very reliable. Okay, if we do surface-to-surface, it's going to be wrong, is what it comes down to. And so that's what's happening here. Now, if we had a star, let's say this is Earth, and this is the sun currently. What happens if the sun collapses down to a much smaller star? You guys may be aware that 5 billion years or so into the future, the sun will run out of hydrogen fuel that it's using now to run nuclear fusion reactions. And after that period there's a period of hydrogen fusion going on now, and then there will be a short period of helium fusion into carbon. And at some point that all shuts down, and the star then, gravitation will collapse the sun. What's going to happen to the gravitational force on the Earth if the sun collapses and you go nothing? Because as long as the mass of the sun remains pretty similar to what it is right now, it's not losing a lot of its mass, it's not ejecting a lot of material. There's not a lot of solar wind taking place with material coming off. As long as the mass is still there, it doesn't need to be of any particular size, it just needs to have the mass, and the distance that we work from will continue to be center to center. So that shouldn't affect the orbit of the Earth, or the orbit of that planet. And then here's the example that we talked about on the previous slide. If we were to hollow out a planet, for example, and place a mass not just at the center. Now there's a symmetry argument that if we place it at the center, the gravitational effects will all cancel out. There'll be no net force of gravity right at the center, but at all locations. So if I move the mass over here, it's a little closer to this stuff, but the stuff it's closer to in angular terms is not as much as the stuff over here in angular terms, and the two effects cancel out. Okay. There's one of the appendices in the book where they go over this, if you're interested in seeing this in more detail. But that's pretty interesting, and the reason this works is because the gravitational force behaves like 1 over distance squared. So because it's a 1 over distance squared force, and because when we move this from one location to the other, the angular amount of stuff on this side and the angular amount of stuff on this side, areas also increase, surface areas increase like r squared, and the two effects balance out, and we get complete cancellation. All right, let's take a look at the vector form of Newton's universal gravitation. Now, we always look at these vector forms first, and then we come back and say, don't worry so much about this, because we're going to be able to use the diagrams to keep track of direction. And so they write these in fancy vector notation, and that's fine, but that's a unit vector, because it has a little hat over the top. And that's keeping track of directions. And again, in really large font down at the bottom that I've highlighted, use the diagrams to show directions, and then all we need are the formulas to find magnitudes. We don't have to try this approach where we're trying to keep track of directions and magnitudes in the same formula. Use the diagrams to keep track of distances and directions, and then just solve for the force. So for example, is this force in the positive or the negative direction? Is this force in the positive or negative direction? And you go, well, if I break it down into components, this is going to have a negative x and a negative y. This is going to have a positive x and a positive y, and we can do that. So we can take these formulas and break them down into components, but it's usually more involved, and it's not necessary. We'll see when we look at examples how this is going to work. So if there's a lot of objects, let's say we have object 1, and we want to come up with all of the forces acting on object 1. Well, object 1 is going to be attracted to object 2, and object 1 is going to be attracted to object 3 and object 4, all the way up to object 1, they call this n, and then we have to do this summation. So all that's saying is that we just have to do vector addition. And we've done that. We did that in the last example. So this is really looking at vector addition of gravitational forces. All right, let's move on a bit here. So we can relate the gravitational constant to the local acceleration of gravity. So this is what I was talking about when I was saying that we have two formulas for gravity now. We have two formulas that we are working from for gravity, and how do they relate to each other? How are the two formulas related? And so what we've got here is, back in chapter 4 and 5, we were using mg as the gravitational force. We said the gravitational force on an object is equal to mg, where g is the gravitational field of the Earth, or the Moon, or whatever planet we're on. The more general formula that we've introduced in this chapter says the force acting on an object near the surface of the Earth would be big G times the mass of the object times the mass of the Earth divided by the distance between the center of the Earth and where the object is located. So what would the distance between the center of the Earth, let's take this book as an example. Let's say that this book is little m, and so that's little m right here. What would r be? And r would be the distance between the book and the center of the Earth. So that would work out to be the radius of the Earth, right? So that's how much distance of separation. Now, the book is much closer to this side of the Earth than it is to the other side. But when we bring all those effects together, not only is this side of the Earth exerting a force on the book, the far side of the Earth is exerting a force on that book, not nearly as much. When we integrate that all together, we can treat it as if all of the force of gravity acting on that book is coming from the center of the planet. It's not. That's not the actual physical reality, but the mathematics works out the same way. Okay, so if we want to take into account the gravitational effect from the entire spherical planet, we use this formula and it will work for us. Okay, so that needs to be the radius of the Earth. That's how much distance there is between an object at the surface and the center. So that says this thing that we've been calling the gravitational field, well, there's an easy formula for it. The gravitational field is not a fundamental property of the universe. It varies. Little g varies from planet to planet. It varies from elevation. You know, the gravitational field of the Earth at the surface does not match the gravitational field of the Earth where the Moon is located. It's different. So if we look at different elevations above the center of the Earth, the values of g are going to be different. And this tells us how to determine for a spherical object, how can we calculate what the gravitational field will be at its surface. So if we want to do the surface, what we can do is put in the mass of the Earth, gravitational constant, and the radius of the Earth. Now if we want to calculate the Earth's gravitational field high above the Earth, we can do that too. We just have to change the distance. Now from this, we were talking about how the masses of Earth, for example, could be calculated. By knowing what the gravitational constant is, by doing those Cavendish experiments we talked about, very high, very careful experiments, very difficult to get these numbers. And then we put in the gravitational field and the measured radius of the Earth, we can measure that. We can use those to come up with a mass. So that's how we measure the mass of the Earth. And then once we've measured the mass of the Earth, we can measure other planets by measuring gravitational effects. Okay, so it just, once we have one object's mass measured, then we can use that to measure the mass of, say, Mars. Mars and Earth have this gravitational attraction. We can take into account, we can see as Mars goes by what effect it's having, and we can determine how much mass Mars would have. So these masses of the planets, that's been something people have been working on for hundreds of years. The Cavendish experiments go back hundreds of years measuring the gravitational constant. All right, so here's the gravitational field, little g. I'm typically, as we did in chapter 4 and 5, those are going to be listed in newtons per kilogram. Here's the formula that we used in chapter 4 and 5. Here's the general formula for gravitational force. And now from that, we can take everything off of this and call it little g. Little g depends on the gravitational constant, depends on the mass of the planet, and it depends on how far we are from the center of the planet. So at the surface, at Earth's surface, we're going to kind of flip this around now. At Earth's surface, this is the mass of the Earth that was measured. This is the gravitational constant. This is the radius of the Earth. That gives us a gravitational field at the surface of 9.83 newtons per kilogram. Now, why, that says versus. So why is it 9.83? Why isn't it 9.8? And actually, at different locations on the Earth, there's an effect of rotation. Now, it's not a gravitational effect, it's a rotation effect. And for convenience, we take into account the Earth's rotation as to how heavy objects appear to be. So when we say that Earth's gravitational field is 9.80, that's not quite true. That's saying that at this location, the 9.83 newtons per kilogram is offset just a little bit, 3 parts in 1,000, and appears to be 9.80. Now, where can we go on the Earth to actually experience this 9.83 newtons per kilogram gravitational field and get rid of the rotational effect? And we could do that at the North Pole or the South Pole. So at the North Pole or South Pole, we wouldn't have to do any corrections. But where we are, just for convenience, we say the gravitational field is 9.80. That's not really true. Part of that is including a rotational effect. All right, this is also stating, example 6.4, the rule says, what about Mount Everest? Can we treat, what would the gravitational field be at the top of Mount Everest at that height? Now, this is a little misleading too, because if you're standing at the top of Mount Everest, you probably shouldn't be treating the planet as a perfect sphere. So if we wanted to treat the planet as a perfect sphere, and then ask, what is the gravitational field 8,850 meters above that perfect sphere, that's going to be a little different from asking what the gravitational field is at the top of Mount Everest. And that's because at the top of Mount Everest, you're also feeling the gravitational effect of Mount Everest. So having all of this stuff close to you adds to the gravitational field. So as you move around the Earth, there are also variations in elevation. There are variations in density of material underground in those regions, and those can also create variations in the gravitational fields. Anyway, we're going to go in and try this. So we're going to say that Mount Everest is height is so small compared with the radius of the Earth that we can treat that as a dr that's been added on to r. In fact, one of the examples that gets used for the surface, the Earth, when people go, well, the Earth's not really spherical. So the Earth, if we treat the Earth as a sphere, how much effect do the mountains have? And the variations from mountains and such, it's like taking a sheet of saran wrap and putting it at different locations on the Earth. So the different mountains and things really do, it's a small effect taking place. So the Earth actually is pretty spherical, okay? The percent differences in different directions are really small. Much less than, I want to say much less than 1% variations in different distances. So what we can do then is, if that's going to be a really small number, what we can do is we can say, well, G is GM over R squared, which is the same thing as big G, big M, R to the minus 2 power. And then we can ask ourselves, how much would the gravitational field vary if we were to change R a little bit? And to do that, we take a derivative. So here is Now it says estimate the value of G. It says the effective value, which is throwing me off a bit. What is the value of G at the top of Mount Everest? So if we increase the distance from the center of the Earth by the 8,850 meters, we can follow this formula. What we can do is say that that small increase in decrease in gravitational field is given by taking the derivative. That gives me a minus 2, big G, big M, r to the minus 3 over dr. That can be written as big G, big M over r squared. Now that's the gravitational field right there at the surface. The additional factor is going to be given by 2 dr over r. So we can write this as minus whatever the gravitational field is at that location times 2 dr over r. Let's put some numbers in here. Big R, which is going to get used here. So the little r now is going to be the radius of the Earth. And for that, I'm using 6.37 10 to the 6th. I looked these things up and they say 6370. It's like 6375. So you'll see this listed as 6.37. You'll see it listed as 6.38. It's one of those numbers that it's easy to round differently. So you'll see a variation from different sources. But my big R, or little r, I guess what I'm putting in here, is 6.37 10 to the 6th. The dr is 8.85 10 to the 3rd. So using this approximation, using the rules of differentiation to find out how much of a difference we might have, that's going to work really well. So the r value, or the little r value here, those are what we're plugging in. That's going to work well. And it says that the variation in the gravitational field is given by that expression right there. And then when I plug all that in, what it's saying is that the gravitational field will vary by 0.00278. Now, I did an inverse of that number. I took that number and just took its inverse. It turns out that it's about 1 part in 360. So we would guess that that would be a decrease of 0.0273. So if we started out with that 9.83 number and subtract this off, that would get us back down to 9.80. So if at sea level, at ocean level, is the gravitational field is 9.83, then at the top of Mount Everest it would be 9.80 are the numbers we're getting. Now what about the International Space Station? The International Space Station orbits at a distance of about 400 kilometers above the Earth's surface. So we could say the dr, the additional distance, is 400 kilometers, whereas the radius of the Earth is 6,370 kilometers. So here, the gravitational field would drop down to 8.70 newtons per kilogram. Okay, so now I'm trying to remember which method I've used here. I think what I did is I took these two. I decided this one was not small enough, so I just added that in, and I should have shown that more explicitly. So yeah, this is the direct method. So I took this 400, added it on to the 6370. This became 6770. That's what went into here. That gave me a value of 8.70. If I use the approximation that I developed over here, I ended up with 8.60. So for the height of Mount Everest, the approximation works pretty well. But if we go all the way up to the International Space Station, hundreds of kilometers, the approximation from the calculus formulas is no longer as useful. I just went back and used the direct formula. I should have added that step here where I took the 400 and added it on to the 6370. All right, here is a table that gives us an idea of how much variation we see. Now remember, this is taking into account Earth's rotational effects. And so the North Pole, well, it's being calculated. They kind of measured it there, right? 9.83. Notice that as you get closer to the equator, the gravitational field drops off. Now the Earth is flattened a bit. There is a little bit more distance when you get to the equator. So you can see that we're getting variations in the gravitational field as we look at different locations. All right, let's look at the effect. Let's look at the effect of Earth's rotation on the gravitational effects. And so to do that, we're going to go back to assuming that the Earth is a perfect sphere. And let's determine what effects rotation have on... okay, here they're saying it's the value of the gravitational field. And I don't want to get that mixed up. So I'm going to say this is the apparent gravitational field versus the actual gravitational field. Now the accelerations, if we're thinking of gravity as creating an acceleration effect, the rotational effect of the Earth is included in that number. Okay, so here's the Earth, here is the planet, and here I got something at one of the poles, here I've got something at the equator, here is the normal force, here is mg. Now at the poles, that's pretty straightforward. At the poles, I'm not accelerating. I mean, at the poles, I'm rotating once every 24 hours, I guess, but there's no acceleration. I'm not going in a circular motion with some radius to it. The normal force, then, will equal mg. And so the g-force, the gravitational field, at that location is 9.83. And when we calculate... oh, that's the equator. That's not, we're done. So at the pole, the acceleration is 0, n is equal to mg, and the gravitational field there, we're calculating that to be 9.83 meters per second squared. Now what's happening at the equator? Well, at the equator, there is going to be a radial acceleration, right? Whatever latitude you're at, except for the poles, you're going to be making these circles, circular motion. Now near the poles, that's not much of an effect, but at the equator, that's like 1,000 miles an hour. You're moving at a pretty good clip. At our latitude here in Oakland, it's something like 700 miles an hour, okay, that we're moving towards the east, okay, so look to the east and say that's where we're headed, and we're headed there like 700 miles an hour as the Earth rotates. Now, here is the acceleration. We've got to represent that there's a rotational effect going on. How are we going to determine that? Well, we can go back and use v squared over r. Now, we've done this before where v is equal to 2 pi r over the period. Let's just derive a formula. So, you know, up until now, with circular motion, we wrote a as v squared over r, but this is telling me I could write a as 4 pi squared r over period squared. Instead of using a velocity each time, which is not always as convenient, it's often it's often easier to use the period of rotation for a planet like Earth. So let's do that. Now the Earth's rotation, rotational period, we've got to be careful about what that means. What does a rotational period really mean? And a rotational period, in order for the Earth to rotate, you guys tell me when I've rotated once. So here I am, I'm Earth, I'm facing the sun, and I'm rotating, and here I am rotating. It's nighttime, and I'm rotating. The sun is coming up, And there is the sun again. How long did that take? And that took 24 hours. But it's not one rotation. And here's why. Not only is the Earth rotating, but the Earth is orbiting. So the sun is off in that direction. I can see it. There's the sun right there. And so what I'm going to do is, this time, I'm going to give myself some space here. I'm going to rotate, but I'm also going to orbit the sun. So by the time I've come around and to the same location, I'm not facing the sun. So it turns out that I need very close to 4 additional minutes, not exactly, in order to rotate a little bit more so that I tip myself so that I'm facing the sun again. Now it makes sense. We set our clocks up for a 24-hour day because our days are based on when does the sun come up and when does the sun go down. But it's not really how long it takes for a rotation of the Earth. So the Earth had finished its rotation here. Now, instead of using the sun as a reference, what we could do is use the stars. If I pick out a very bright star and I face it, and then I set the clock and rotate, then the orbital motion has a negligible effect. The star is so far away that by the time I've completed one rotation, the star is back in the same place. And so if we use the stars as a reference, what we find is the Earth rotates in 23 hours, 56 minutes, and 4 seconds plus some fractions of a second. So that works out to 86,164 seconds. So it's, 4 minutes short of the 24-hour period. Anyway, I don't know if that level of detail was essential, but I think it is useful. I think it's very useful to think in terms of coordinate systems. And if you've got a planet that's rotating and orbiting, that's going to make a difference on length of day. The length of the day is not really a rotation. It's a rotational effect plus, it's an orbiting effect plus a rotational effect, which I guess I said that the right way. So it's a rotational effect plus the effects of the orbital motion. So anyway, I'm going to put in this corrected, modified, more accurate number. And what it says is that the acceleration due to standing on the Earth at the equator is 0.0339 meters per second squared. So it's a tiny fraction of the gravitational field, but look, there is the 0.03 effect that we've been talking about. Now if you're at our latitude, what are we at? We're like at 38 degrees north latitude. I can take that number, multiply by the cosine of theta, and the cosine of the latitude will tell me how to adjust the acceleration number for a given latitude. And so what happens then is when I look at objects sitting at the surface here, there's a normal force, there's a gravitational force, but since there's an acceleration here, the normal force is not as large as the gravitational force. The gravitational force is larger, and we can calculate that by looking at the acceleration effect and saying the acceleration is due to the net force being mg minus n over m. If I solve for the normal force, it becomes mg minus a. That's the acceleration effect being combined with the gravitational force effect. And so let's call this g prime. Effectively, what gravitational force field does there appear to be? And it appears to be 9.80. Okay, so there's the decrease in the gravitational field, the apparent or the effective field once we've included in the acceleration effects. All right. Okay, so I'm thinking we're getting close here to where we want to finish up for the day. Where's a good place? Let's look at this other topic here. So here's some satellites, and we're going to go after that topic of weightlessness. What does it mean to be weightless? And you look at astronauts in the space station, And you can see they're just floating around. Does that mean that there's no gravity? And you go, no, there's absolutely gravity. Gravity is holding the spacecraft in orbit. If there were no gravity, if we turn the gravity off at some point, spacecraft would head off in a straight line. What's happening is the satellite is in free fall. So the satellite is in free fall, the astronauts inside are in free fall. It's kind of like that elevator example we did back in chapter 4. If somebody's in an elevator and we cut the cable, you know, have your friend go up and cut the cable on the elevator, then the elevator accelerates at 9.8 meters per second squared, and you accelerate at 9.8 meters per second squared, and as a result, if you're inside the elevator, you feel weightless. Now the gravitational force is still there, but if you took the bathroom scales and went into the elevator, and if you try standing on the scales now, the scales read 0 if you're in free fall. So that's where the weightlessness is coming from, is that these objects are in free fall. Now if they're in free fall, why don't they run into the Earth? And that's because we've given them enough velocity in a forward direction so that even though they're falling, even though there's a radial acceleration taking place, their trajectory takes them over the horizon of the Earth. So yeah, they're falling to the Earth, but they're moving forward at such a high speed, they keep missing the Earth. And instead of hitting the Earth, they end up in an orbit. They keep getting drawn towards the Earth, but they never hit it because of their speed. So, and this is why I stay away from, once we're talking about weightlessness, that's fine. So here is the satellite, here's the satellite, and without gravity it heads off in this direction. With gravity, we give this just the right speed so that with gravity, the curvature created by gravity creates an orbit. Now it turns out that as long as we get up above the atmosphere, there's a fairly wide range of velocities that will put it in some kind of an orbit. There's only one particular velocity that will give us a circular orbit. Other velocities might give us an elliptical orbit where the velocity is changing in different parts of that orbit as we move along. So that's the idea of getting something into orbit. Now we're pretty much going to be looking exclusively at circular orbits, and that's going to allow us to come back and use our formulas for circular motion. So here's an example, and what it's saying is, let's imagine a geosynchronous satellite. So we have a geosynchronous satellite. The satellite is one that stays above the same point of the Earth, used for television, radio transmission. So let me skip ahead. We're clearly going to have to come back and start from this slide right here. So we will plan to do that. But let me just get the diagram set up here. So here's the Earth, and the idea of a geosynchronous orbit is that as the Earth rotates, the satellite proceeds in its orbit in a manner where it stays right above the same point of the Earth. So that means that the period for a geosynchronous satellite needs to be equal to the period of the Earth's rotation. So, and here we go. So here is the geosynchronous stuff. So yeah, this problem, it's fairly involved. We do want to start looking at orbits, so maybe we'll just stop right there. So this is, I guess where we want to start from is here. We want to start thinking of circular orbits. For a circular orbit, how is the speed going to be related to the orbital radius? And how can we go in and calculate forces and determine accelerations for circular orbits around planet Earth? So that'll be a good topic for us to come back and look at in some detail. So I'm going to stop there. If you guys have questions, stop by office hours. We will get those looked at.